Okay. Next we look at some terms. I ask everyone to listen carefully. These things you have to remember. First, look at the successor router. A cost is identified here. This is for the convenience of everyone to understand. Actually, strictly speaking, a metric should be marked here, because it is not called cost in EIGRP. Called metric. But the meaning is the same. The cost value above is a total of 40. 10 plus 30 equals 40. The following cost value is 20 plus 30. A total of 50. That is to say, it must be the above route, because its overall routing metric is smaller. This protocol mechanism is consistent with what we said before. Both lines learned via EIGRP. The overall measure of the above line is smaller. Just take the above route. That is to say, now if going to 4.4.4.4, logically, it should go like this. This is called the main line. This is the line going in and out now. The lines that appear in the routing table will definitely be added to the table, because it is the best path. Then, for this optimal path, it has a thing. Successor router. Successor router means, if the current main line is the above line, then take R1 as an example. R1 goes to 4.4.4.4 and takes the above route. For this optimal route, the next hop router of this optimal main line. Successor router. R1 if going to 4.4.4.4. Give traffic to R2. It is the successor router to the route entry 4.4.4.4 on R1. Because only the optimal route is added to the table. It is the successor router of this route. Certainly. This is all for R1. It's different if you change the device. Looking further down is the feasible distance. From R1 to destination network 4.4.4.4. The optimal total metric for this route. That is 30 plus 10 equal to 40. Further down is the advertised distance. Advertisement distance has two words. One is RD. One is AD. But we basically call it AD. It's just a title. Don't need to bother with it. Still, for the device R1, the advertised distance refers to the R1 going to 4.4.4.4 in the future. Its successor router. That is R2. Feasible distance to destination network. The advertising router refers to the R1 now reaches the route 4.4.4.4. Feasible distance for its successor router to reach 4.4.4.4. That is 30. That sounds a little boring. And not easy to understand. I try to keep it as simple as possible. For example, there are 3 locations. Suppose this is A, this is B, this is C. It means A to B is 10 meters. B to C is 20 meters. Then A to C is called its feasible distance. B is the successor router of A. Feasible distance from B to C is called the advertised distance of A. Okay. Further down is the feasible successor router. Let's not talk about this. Let's talk about the feasible conditions first. Because only after the feasible conditions are met, there is a successor router. So let's start with the feasible conditions. The feasible condition is, if now there is a path, it can satisfy a parameter. We call it an alternate path. The AD of the alternate path is now less than the FD of the main path. Then it can be a qualified alternate path. Let's take this picture as an example. Now the following line. Its alternate path is the following line. Because the above is the main path. AD is the advertised distance. If its next hop router is R3, This is called its advertised distance. Is 30. So now the FD of the main line is 40. 30 is less than 40 now. Suppose you use it as a backup line. Then you compare. Now indeed its FD is smaller than the main line. Then this path can be an alternate path. So what we're talking about? It is a feasible condition, called FC. If this feasible condition is met now, then the following path can be a backup path. Then it can go into the topology table. Then the next hop router on this backup path. Feasible successor router. Real mainline router. Successor router. The next hop router on the backup line. Feasible successor. Then the condition for generating a feasible successor router is the line must now be available. That is, if the current route satisfies the feasible condition, it becomes a backup line. Then this router will become FS. Feasible successor. Here are some features between them. That is to say, for a line, we have to compare such values. If this value is not met, it cannot enter the topology table. I want to ask you a question now. If it's not 30 now, I changed it to 40. So now in this path, is there still a viable post router? I saw someone ask how to choose a backup link when there are 3 lines. The same. If the 3 lines, you calculate again. As long as it is now eligible, it also enters the table. That's just in the topology table. Middle line. It will also be compared with the following lines. If both of them are exactly equivalent, then they are loads. If they are not exactly equivalent, because we'll look at 2 parameters later, they are hardly completely equivalent. As long as feasible, it becomes the backup line. Feasible successor. So now if the cost here is 40, then this path will have no backup path. Then look down. This is Cisco's metric. This 5K refers to 5 values. We haven't learned some settling yet. You can think of this K as it is 5 values. Assume that respectively the bandwidth, reliability, delay, load, maximum transmission unit. Then there are 2 values in each value. 0 and 1. 1 for reference. 0 means no reference. That is 1 for sure. 0 means negative. For EIGRP, it can refer to 5 parameters. Let's learn EIGRP for beginners. Only focus on 2. 1 is bandwidth. 1 is delayed. Usually. Reliability. Loading. And MTU. We often don't think about it. For OSPF, just refer to the bandwidth. EIGRP reference 5 options. If we refer to bandwidth, then this one is 1. If the reference delay, then it is 1. Others do not refer to 0. Then this 5K value is 10100. This means we refer to bandwidth and latency without reference to the other 3 parameters. 5K is 5 reference factors. Refers to the 5 values. By default, EIGRP only refers to bandwidth and delay. Others are not referenced. The following is the calculation formula of metric. Everyone can take a look. 256 times 10 to the 7th power divided by the minimum interface bandwidth of the link. Add the sum of link delays and divide by 10. So there are actually only bandwidth and latency in it. This is a default calculation formula. Therefore, we generally do not refer to other. 5K is 5 values. It represents the reference switch. Reference is 1. No reference is 0. When you reach the NP stage, you will learn the message. That is, all packets of EIGRP. You will both get packets. Then look at the fields one by one. Then you will see the values of 0 and 1 in this 5KR. Next, look at the message. Let's not look at the fifth. In fact, the fifth is not a real message. There are 4 EIGRP packets. Hello, update, query, and reply. Hello is to establish a neighbor relationship. Hello packet. I just introduced it to you. If the two routers are now directly connected, once EIGRP is announced, the two interfaces will start sending hello packets to the outside world. They both send each other. Then one of the devices receives the other party's hello packet. The two of them will establish a neighbor relationship. They start to learn routing from each other. Certainly, you need to declare this route yourself. That is to say, for dynamic routing protocols. Generally, there is the concept of neighbors. Only after establishing neighbor relationship can we learn from each other. I just said that too. They are hello packets sent every 5 seconds. 15 seconds if not received. The neighbor will fail. The second message is update. Send routing update. It represents 2 dots. The first point is when the device establishes a neighbor relationship. For the first time, all routes will be updated to each other at one time. The first packet is also a packet passed by the router. Because the other party has nothing about me now. Then the message sent to the other party for the first time. It is the content carried by the update message. Secondly, if there is an update in the future, also known as sending routing updates, it is also an update message. Then EIGRP sends the routing table. Give an example to explain the third and fourth. Let's draw a picture. 1, 2, 3, 4. This is 4 devices. Device 4 has a network segment here. Assuming this has an exact address. 4.4.4.4. So now running EIGRP. Device 2 can learn device 4 here. Because device 4 interacts with device 3. Device 3 interacts with device 2. Device 2 has this 4.4.4.4 route. At that moment, device 2 and device 3 were disconnected. Whether it is an interface problem or line problem, they both broke. So first for device 2. The next hop that device 2 originally went to was device 3. So now device 2 will have a consideration. It will think that now because there is a break between the two of them, neighbors fail. 15 seconds passed. It found lost this neighbor. At the same time, it thinks that the relationship between this device and it is broken. And it also thinks it has a problem now. Then this route will be gone. In addition to losing this neighbor relationship, the route to 4.4.4.4 will also be lost. But for EIGRP, now device 2 will not immediately delete this 4.4.4.4 from the routing table. It will give its neighbors who are still send a request message. So now it has only one neighbor left. It will send a message to device 1. It will ask if device 1 has a method path to 4.4.4.4. Then device 1 will reply to device 2 that it does not. If it wants to go to 4.4.4.4, it has to rely on device 2. Then device 2 will send 16 times per unit time. Device 1 needs to reply to it 16 times no. After that, device 2 will delete it. But there is a situation. For example, originally, device 1 and device 4 were directly connected. Then device 2 goes to 4.4.4.4 and goes to the right. This is its optimal path. And possibly for some reason, this route has not been added to the topology table. Then at this time when it is broken, it will query device 1. Is there a route to 4.4.4.4? Then now device 1 will reply that it knows. Device 2 will send the next hop to the route 4. 4.4.4. Pointing to device 1. Then complete the data forwarding. This is called sending a request to a neighbor. Inquire. And the response. This is the interaction between them. Finally, there is an ACK. It is not a message. It is a confirmation mechanism. Then in the 4 messages mentioned above, there will be an ACK field. Can be filled with it. That is, all messages of EIGRP provide confirmation mechanism. After the device sends data to the other party, the other party can carry the confirmation. In the message sent to the device, represents that the message between them has been transmitted to. It is equivalent to a confirmation mechanism. When you analyze the message later, you will say, now just to briefly mention to you. Okay. We are about to enter the configuration phase. First turn on these 4 devices. Save some time. Let's go back to what we just said. EIGRP now wants to establish neighbors. Then establishing a neighbor is conditional. There are 3 conditions. The first one is that the AS number must be consistent. Because now we use EIGRP as an IGP protocol. So it does not involve the establishment of relationships between AS. So now the AS number must be the same. Secondly, 5K must be consistent. It doesn't mean the bandwidth and latency of the 2 interfaces must be the same. That's not what it means. Not the specific value inside. But 5K, this 10100 must be consistent. 2 devices establish a neighbor. The parameters they refer to must be consistent. One of the device reference bandwidth and latency. The other can only refer to bandwidth and delay. Finally, the authentication must be consistent. Certification means the messages exchanged in the device provide authentication. It is equivalent to choosing an authentication method now. It is a means of encryption. The devices at both ends are up with the same authentication method. And both parties have a password. When exchanging messages between them, it can carry the authentication method and password for transmission. The authentication parameters in both of them must be the same to build a relationship. So why do it? For example, I have a hack. I can simulate a hello message. Then I sent you a message. I can pretend to build a neighborhood with you. You can tell me your information. Then I can know the overall information of your network now. At least it is possible to calculate the network topology. There is no problem. Now I will establish a neighbor relationship with you. We start to calculate. Because in the future we learn the overall network topology. We are going to calculate the route ourselves. Then the overall topology. I can learn. So you will find. I can break into you. This is very common. But if you want to build a neighborhood with me now, then in the message you sent, must be consistent with my authentication. I use some kind of encryption algorithm. Verification method. You must also use this method. And with the same password. Otherwise, our relationship cannot be established. It will cause the 2 of us to be unable to send messages. But by default, we do not certify. Okay. Then we're done with the theory part. We're starting to get into the experimental part. Let's take a look at the overall configuration. We have joined two serial lines here. Everyone can see. Below is the serial port. First of all, for R1, we first need to give the device a name. R1. After naming, we're going to start with the configuration part of the IP address. Let's do a configuration now. 12.1.1.1. Then enter the S10 interface. Enter the interface. We also go to address configuration. 13.1.1.1. Let's configure it. This is our 2.0.0 interface. Now you should have no problem with address configuration. This address is 24.1.1.2. I now ask you a question. Think about it. Above this is an Ethernet link. Because we are using the Ethernet port, the serial port is used below. Then I ask you a question now. For example, after a while, all the addresses are configured. I ping R1 and R4 respectively from R2. I also ping R1 and R4 here in R3. May I ask when R2 and R3 ping the two devices for the first time? Will packets be dropped? If you have an answer, you can write it on the barrage. During my configuration, you can think about this simple question. S10. The address is 13.1.1.3. (34.1.1.3). Then R4. S11. 34.1.1.4. The last one. Up a loopback port on the device R4. Configure it with an address. 4.4.4.4. Mask is 32 bits. We are done configuring. Then do a test. We choose R2 and R3 for testing. Then the thought question just now. I believe you already have the answer. Then let's talk. R2 goes to ping first. Ping 12.1.1.1. See if I can get through. Okay. Pass. Dropped packets. Let's ping again. Ping 24.1.1.4. Okay. It also drops a packet. Prove that R2 and R1 R4 are connected. Let's ping on R3 again. Ping 13.1.1.1. It will not drop packets. 5 all passes. Ping 34.1.1.4. It's also all pass. When we talked about the second floor, actually told you. Interfaces actually have types. According to the protocol stack, there is an interface called Ethernet port. What you see now on the LAN. All networking projects. The E port you see is called the Ethernet port. 10M. F port is fast Ethernet. 100M. G port is gigabit Ethernet. 1000M. That is 1G interface, including XG port. 10G. These are Ethernet ports. Running the Ethernet standard. The Ethernet standard is, by default, the switch can be connected in the middle. Then based on this standard, means now inside a network, there may be multiple devices. We need to be on a link, uniquely targeted to a device. For example, I want to communicate with you. Then we must request the other party's MAC. That is, we need an ARP. Let's broadcast first. See where this address is. I can communicate with you only after. This is called the communication standard in Ethernet. You need to make an ARP request. Then when you send the message, packets will definitely be dropped. Then when you sent the message for the first time, you must have timed out the request. Because you are now doing an ARP reply. There's no way you can come back in time. So it times out. So why isn't the packet dropped below? The following is the S port. It is a serial port. Serial port is a technology used in wide area network. That is, interface type under WAN. We don't use. Then its typical characteristics are peer-to-peer. Means there is no switch in the middle. There can be no other equipment connected in the middle. I don't need to request your MAC. I don't need to do ARP. I will not send ARP packets. Packets will not be dropped. Because I sent it to you. I will reply immediately. Will not request timeout. Next we are going to start configuring EIGRP. Very simple. Let's first look at R1. If we want to configure, definitely need to enter configuration mode. After entering configuration mode, we're typing router EIGRP here. Then enter a question mark. Here you can see an as autonomous system. This is called as number. That is, in EIGRP. Here is also to specify the AS number. But here it is written EIGRP 100. All four devices are consistent. We put 100 here. This is equivalent to, you give the autonomous system of EIGRP a name. But if we now configure, must be within an autonomous system. We now configure it with 100. Specify an AS number. The following word. EIGRP not only supports AS number, it also supports naming. This thing will be more complicated. When you arrive at IE, you will speak. Then when we enter the routing view of EIGRP, must first enter a command. Please pay attention. We must first turn off auto-summarization. No auto-summary. This command is very important. If you don't enter this command, then this will be enabled by default. There are many commands enabled by default in Cisco. You must remember each. No auto-summary is to turn off automatic summary. This automatic summary is what I just told you. 172.16.1.0 bar 24. This is a Class B address. If you don't turn off automatic summarization, it will spread to you. 172.16.0.0 bar 16. For example, I am on the device R1. A network segment of 172.16.1.0 bar 24 is connected. If this network segment is declared in this EIGRP, but the automatic summary is not turned off. Here at R4, what it learns is 172.16.0.0 bar 16. I learned it wrong. So this command must be entered. After turning off automatic summarization. It's a normal announcement. For EIGRP, it declares in 2 steps. The first step is to establish a neighbor relationship. That is, R1 and R2 are directly connected. They both run EIGRP. Declare the directly connected network segment. R1 declared. R2 also declares. Since the interface of R1 and the interface of R2 are in this segment, so just declare this network segment. This interface will be declared in. EIGRP starts to send hello packets out. The left interface of R2 is the same. So if we are using EIGRP to declare, first declare your direct connection. As long as the device wants to establish a neighbor relationship with the peer, the two ends must declare direct connection to each other. This is the first step. The second step is to pass the route. The reason for establishing a neighbor relationship between devices. It is because there is a network segment that wants to be passed to the other party. I will give you a simple explanation. If we don't use dynamic routing, we use static routing. You need to manually enter. Now, as long as the dynamic routing protocol is running, we only need to establish a neighbor relationship with each other. I declare a 1.0 network segment on R1. All devices can learn. This is the difference between dynamic and static. If this 1.0 network segment is gone, R1 will send link status updates to other devices. All devices will delete this network segment. This is the purpose of the declaration. Then we start declaring. The declaration is called network. We enter a 12.1.1.0 here. Then here. Let's make a positive announcement first. For example, 255.255.255.0. After the announcement, let's check. Do show run. Check router EIGRP. Is this command? Look. See what I have configured for my EIGRP. I am on this device. First up an EIGRP 100. And I declared a network segment of 12.1.1.0. Everyone can see. Right 0.0.255 behind. But the network I just entered, it seems to be 12.1.1.0. 255.255.255.0. Why did it become like this? Isn't this a bit strange? Well, first of all, you need to know. This thing is called a mask. This thing is called a wildcard. Wildcard mask. The mask we're talking about is the subnet mask. Mask is the kind of continuous 1 and 0. And 1 in the front and 0 in the back. 1 means an exact match. Is the network bit. 0 means no matching. Stands for random. Is the host bit. So before talking about wildcards, let's look here first. 3255 and 10 represent 24180. 30 and 1255 represent 24 and 81. Actually, you can temporarily understand it as an anti-mask. In the NA stage, just understand it as an anti-mask. Anti-mask is consecutive 0 and 1. And 0 is in the front and 1 is in the back. 0 and 1 cannot be interspersed. 0 means an exact match. 1 means no match. That is random. This is called anti-masking. It's the exact opposite of what we call a mask. So what are wildcards? The NP stage of this thing will focus on it. Wildcards can be shuffled. It is a mask that can jump. Wildcard mask can be a combination of scrambled zeros and 1s. Then 0 means an exact match. 1 represents random. Here is actually a wildcard. But at this stage, you can understand it as an anti-mask. Here are some differences between them. So for us, actually, we need to declare its mask via wildcard. But if you declare a positive mask, it will automatically give you the input in the form of wildcards. You will do data capture in the future. When including some strategies, use it often. ACLs including the NA phase also use wildcards, but also consecutive zeros and 1s. For R1, I just made an announcement. Then I will redeclare here. For example, network 12.1.1.0, 0.0.0.255. Let's change it. It doesn't matter whether you change it or not. But it's better to change it. We want a correct declaration. Then we also declare. Establish a neighbor relationship with R3. Then declare 13.1.1.0, 0.0.0.255. So for now, we're actually done. R1 is now declared. Direct connection with R2 and the internet segment of R3 have been declared. Then it is time to declare the network segment behind. But R1 has no network segment, because there is only one network segment behind R4. So R1 is actually done. Then take a look here at R2. We also make a configuration here. For R2, we're also going to start announcing. Then, before announcing, we must first router EIGRP 100. Afterwards you must turn off its automatic summarization. Next we declare. I'm here to show you a declaration. Network 12.1.1.0, 0.0.0.255. This is to establish a neighbor relationship with R1. So when I press enter now, everyone can observe the phenomenon. It plays the log here. Now R2 has a new neighbor. 12.1.1.1. Its interface is E00. Is up. Then it is 12.1.1.1. Since we were just now on this device. Declare interconnected 12 network segments. R2 now also declares. So when R2 declares, it sends packets out. So at the same time, R1 can also receive the data packets sent by it. Then R1 will know. Now there is a neighbor. 12.1.1.1. This is its interface. Then when they become neighbors, we'll find out. There will be a bond between them. Then they can exchange information with each other. Okay. We'll stop here. Then we also hope that students can follow us. We are ThinkMO Education. I'm Grolin Annesley from ThinkMO. I hope today's content is helpful to you. See you next class. Bye classmates.